So going back to our result that we have mentioned last time, we would like to establish that this LP space, this Lebesgue space equipped with this function is indeed a Banach space. So it is a complete norm space. To establish that, okay, let's start with a lemma first. And let us show that this is indeed a vector space. So the Lebesgue space LP x sigma mu, so that's the measure space. Okay, this is a vector space over the field K. So whatever the field for the Banach space Y, that would be the field for this Lebesgue space. For P 1 to infinity. So let's start the proof. It is natural to separate the cases. So suppose P is equal to infinity. So in this case, we have, but before going to these cases, let us take note that, okay, since or note that from the homogeneity, which we have shown already, of this function called pxy, again, not emphasizing the sigma algebra and the measure, it follows that alpha f is in LP. Okay. For every f in LP and for every scalar alpha. Of course, one has to check strong measurability of alpha times f, but that can be easily shown. Okay, so alpha times f is strongly measurable, and the value of this with respect to this function is finite according to homogeneity. Because, so going back to that remark here, so for in the first remark, so if f is in LP, this is finite, therefore this product is also finite. Hence, the norm or the value of this with respect to the function double bar sub LP is finite. Okay, so that is one course case in showing that this is a vector space. Here we only need to show that it is closed under scalar multiplication. I mean LP is closed under scalar multiplication, and it is closed under addition. Because you can consider this as a subspace of functions from x to y, and take note that the collection of functions from x to y is a vector space over K. Hence, you can consider LP as a subspace of the set of all functions from x to y. And you only need to apply the subspace test. In other words, closure under scalar multiplication and closure under addition. Okay, so going back to the cases. So the first case, suppose that P is infinity. Then F plus G is mu strongly measurable. You can also show this. And the proof is similar to the case of, let's say, to the case in real analysis for measurability. And okay, one can find, let's say, null sets NF and NG by definition of L infinity. Okay, so null sets means that the measure of these two sets are 0. And okay, so f of x, okay, is less or equal to, let's say, the norm of f as a bounded function, and f y. But we can choose this null set in such a way that this is in fact the L infinity norm, according to the second remark a while ago. Okay, here I am already saying that it's a norm, but we haven't verified it yet. So with respect to this value, okay, for any x except on the null set NF. Okay, you do that also for G. So we can choose this null set N sub G in such a way that this norm is equal to this value here, xy, of course here, all x in NG. Okay, to have a common ground, then if I define N to be, let's say, NF union NG, this is in the sigma algebra, and applying subadditivity of the measure, the measure of this is 0. And by the triangle inequality, you can see that this is less or equal to, okay, the sum of the norm is less than or equal to the, or the norm, the sum is less than or equal to the sum of norms. And then this is less or equal to, according to this two inequality. Note that these are now applicable since x is neither in NF nor in NG. If it is in x minus n, okay. So you have here this value with respect to f, and this value with respect to y. Since f and g are both in L infinity, these are finite. Okay, so this means that f and g are, f plus g is essentially bounded. Thus, f plus g is also in L infinity. Okay, so that's the easy case when p is equal to infinity. The second case, what if p is finite? Okay, so case 2, what if p is greater or equal to 1 but less than infinity? Let us consider the following elementary inequality. So for any two real numbers a and b, if I take, let's say, the absolute value of the sum, okay, this is less or equal to, let's say, what? The sum of the absolute values, okay, by triangle inequality. The power function here is monotonic, so you can raise this to p. And then the sum of the absolute values of a and b is less or equal to the twice of the max. Okay, So either term is less than or equal to the max, so therefore the sum is less than twice the max raised to p. And you can check that this is 2 raised to p max. Now, if the max is the magnitude of a, then the max raised to p is the maximum between these two quantities. And of course, this max, well, the max is either this or this, and obviously that would imply this estimate. So the max is less than the sum. Okay. So applying this, just take note that this is again strongly measurable as before. And if you take, let's say, the value of this with respect to this function, okay, the candidate norm. To simplify things, take note that this is finite if only if the power, this number raised to the power p is also finite. Okay, just to simplify the computation without resorting into the roots. Okay, so by definition, this is the integral of the norm of f plus g raised to p d mu. Okay, and if I apply the triangle inequality, this is less or equal to the norm of f plus the norm of g raised to p, but this is non-negative, so we can raise that to the power p and then take the absolute value. Okay. Now it is clear here that we now take a to be the norm of f and b to the norm of g. Or more precisely, if you want to put the arguments, a is the norm of f of x and b to be the norm of g of x. Then applying the above inequality, we would get that this is less or equal to 2 raised to p times. Okay, here I will now apply the linearity of the Lebesgue-Bochner integral. So this is the norm of f raised to p d mu plus the integral over x of the norm of g raised to p d mu. Since f and g are in LP, then this is finite. Thus, the sum is strongly measurable, and this value is finite. Therefore, the sum is also in LP. Hence, as mentioned a while ago by the subspace test, when the Lebesgue space LP is viewed as a subspace of the vector space of functions from x to y, we conclude that this Lebesgue space LP is also a vector space. Okay, so that's the first part. Next, we show that indeed this function here is a norm. That would be the next lemma. So this is a norm on this Lebesgue space. Of course, for p from 1 to infinity. So again, let us split the proof into two cases. If p is infinity and if p is finite. Okay, so when p is equal to infinity, going back to what we have established here, okay. So let us emphasize this part here. So we have a null set, okay, in this case n, wherein the norm of the sum is less or equal to the sum of these L infinity values. Okay, because the L infinity of f plus g is the infimum, so this quantity is less or equal to this one. Okay, so from this statement here, okay, let us call this asterisk. Okay, from asterisk, and the definition of the essential supremum, or this function here, we already obtained that we can already obtain that the uh, value of the sum under this function is less or equal to the sum of the corresponding values. Okay, so take note here that it remains to show the triangle inequality, because we already established homogeneity and definiteness a while ago. Okay, so that's the easy case again. Now, what if P is finite? So for this, we need the so-called Holder's inequality. So those who are familiar with Lebesgue integration theory, this is what we need to prove the triangle inequality for the Lebesgue spaces, or for the function, for this function in the case of Lebesgue spaces. So let us state this one. So take three numbers, let's say P, Q, R, 1 to infinity, such that the sum of the reciprocals of P and Q is equal to the reciprocal of R. Here, we follow the convention that 1 over infinity is equal to 0. So for instance, if R is equal to infinity, then, or let's say R is equal to 1 and P is equal to 1, then this equation is satisfied for P equals 1, Q equals infinity, and R equals 1. R equals 1. Okay. So that is our convention to make this formula work even in the case where at least one of these PQR is infinity. Okay, suppose I have an P function, okay, without emphasizing again the measure, and then an LQ function, xy, then the product of the norms. So here the norm is taken with respect to y, is in L R of x. Take note that this is space when y is taken to be R. Okay. So take note that if, let's say, y is the field of complex or real numbers. So if, let's say, y is either, so if y is equal to k, then the product is also in LR. let's say LRX. Okay. In fact, this is valid when, let's say, Y is a Banach algebra. Okay. So a Banach algebra, is a Banach space wherein there is a multiplication operator. Okay, so that this is well-defined process. Okay, so in general, for Banach spaces, there is a concept of scalar multiplication, but there's uh, not necessarily, or there's no notion of multiplication of vectors necessarily. So for Banach algebra, there's a concept of vector multiplication. Okay, so you can take the product of two vectors, and this product should be associative and distributive over vectors and over scalars. Okay, and if you are so let us write that down for completeness. So that is to exist an operator that takes a pair and then it will output the product. So this is a function from, let's say, y cross y to itself. That is associative. So let us put it here. Associative, meaning x, y, z is equal to x, y, z, and yeah. For any, of course, let us put down here x, y, z, y, distributive. So x plus y z times z is equal to x z plus y z, and let's say x times the quantity y plus z is equal to xy plus xz. And it is also distributive in this sense. So alpha x y is equal to the quantity alpha x times y, and this is equal to x times the quantity alpha y. Of course, here alpha is a scalar. And finally, the product of the norm is less or equal to the norm of the products. Okay, so this note is also valid even in the case where y is a Banach algebra, so that you have a notion of vector multiplication. Okay, however, in general, for a general Banach space y, if you do not have a notion of multiplication, so one can only postulate the product of the norms. Okay, because in this case, the norms will now be real numbers, hence the product in this part here is well defined. Okay, so that's Holder's inequality. So for completeness, let us, and for the sake of the others that who are not familiar with the proof, let us consider or take a look at the proof. So this is the proof of the Holder inequality. Let's start with several, or let us split the proof into several steps. Step 1, what if, let's say, if P is equal to 1, okay. Recall that here we have this equation, the relationship between P, Q, and R. So if P is equal to 1 and Q is equal to infinity, then we are left with the case that R is equal to 1. Okay. If this is the case, then okay, for mu almost every x in the domain, if I take, let's say, the product of the norms of f of x and g of x, take note that this is the norm in y. This is less or equal to, okay, let's say f of x, okay, times the sup or the L infinity norm, okay, of xy. So the essential sup is greater or equal to any value almost everywhere. Okay. You can also justify that this is measurable. Okay, since f is measurable, here by measurable, we mean with respect to the Lebesgue measure, because we are now taking the norm in y, Lebesgue measure in r. So this is, let's say, if we denote the Lebesgue measure by lambda 1, okay. So this is lambda 1 measurable, where lambda 1 is the Lebesgue measure in r. Since f and g are mu is strongly measurable, and take note that the norm function from y to r is continuous. And last time we established that the composition of a continuous map and a strongly measurable function is also strongly measurable. Okay. Here, we did not emphasize strong measurability because the set of real numbers is separable, and for separable images or target spaces, strong measurability and measurability are the same. Okay, so that is measurable. And if we take therefore the, or if we compute the L1 norm, okay, of this product, this is by definition the integral over x, the norm of f, norm of g. Okay, so let us emphasize the argument g of x, d mu of x. Okay, and if I use this, this is now constant with respect to x, so this is less or equal to the integral of f of x d mu of x times the L infinity norm of g. Okay, but then we can replace this quantity here by the L1 norm of f. And disprove the case. Take note that, okay, this is R. And Q is equal to infinity. And P is equal to 1. This is the statement on the holder's inequality with these specific values of P, Q, and R. Okay. And you can also proceed in a similar fashion when the roles of P and Q are reversed. So you just need to here take the L infinity norm of F instead of G. So the proof is similar when P is equal to infinity, Q is equal to 1, and R is equal to 1. Okay, so this will establish the case when P is equal to 1 and P is equal to infinity. Now, so what would be the second step? The second step here would be, what if P is finite? Okay, let us still consider the case where R is equal to 1. So in this case, Q is now 1 minus 1 over P, or I should say 1 over Q. So by definition, 1 over Q is 1 minus 1 over P. Okay, and if P is finite, greater or equal to 1, one can see that indeed Q is also between 1 and infinity. Okay. So to prove the next step, so if either, let's say, let us consider special cases. So if either this value is 0 or the one with G, so LQ is 0, then either F is equal to 0 mu almost everywhere, or G is equal to 0 mu almost everywhere. Okay. Thus, this implies that the product of the norms, either case, is equal to 0 mu almost everywhere, and the Holder's inequality, so and the Holder's inequality trivially holds. In fact, both sides of the inequality is equal to 0. Okay, because if this is 0, then the L1 norm or the LR norm is 0, and the product is also equal to 0. So going back to that inequality here, okay. There's no inequality. Okay, so let me put that one, and here the LR norm of the product is less or equal to the product of the norms. Mhm. Okay, so this is all Holder's inequality. So I apologize for that one. There should be an inequality, but it was not stated a while ago. But this is the inequality that we are referring to. Okay, so that is the easy case, special cases. So let us suppose now that neither the norm of f nor the norm of g is 0. So let's say this is positive. And this is also positive. Well, let us recall Young's inequality. So in analysis, there are several inequalities. Okay. The product of two functions is less or equal to this sum, 1 over p times a raised to p plus 1 over q b raised to q. Okay. So a and b here are non-negative. P and q, let's say so 1 over p plus 1 over q is equal to 1. Okay, this is the case because r is equal to 1. Well, to know it, or to know this, or to show this, I should say, note that the log function, here I'm referring to the natural log function, the set of positive numbers to r is concave. Since if you take, let's say, the second derivative of the log, this is equal to 1 over x squared. This is negative for any x in your domain. Okay. Hence, what do we mean by this concave? So the log of, let's say, the log of the linear combination, so theta x plus, let's say, 1 minus theta y is greater or equal to theta log x plus 1 minus theta log y. So that is concavity, the opposite inequality for convexity. Okay, so according to this concavity of the log, if I take the log of the product, here, of course, a and b must be positive. Okay, but take note that if a is 0 or b is 0, then this inequality is trivial because the left-hand side is 0. So suppose a and b are positive. Okay. The log of the product is the sum of the logs. And the log of the power, a raised to p. So to cancel the power, we need to multiply 1 over p. And then similarly, in this case, 1 over q log b raised to q. Now you could see immediately, if I take this to be theta, I take this to be x, I take this to be y, and this 1 over q is now 1 minus theta, because the sum of the reciprocals of p and q is equal to 1. Okay. In other words, they are convex conjugate. Then using the concavity of the log function, this is greater or equal to 1 over p log of or I should say log of 1 over p a raised to p plus 1 over q b raised to q. And then take the exponential both sides. Okay. This should be less or equal. Okay. Take note of this inequality. It should be the other way around. And then if you take exponential, then you end up with Young's inequality. This one here. So let us highlight this inequality. Okay. So you want to prove Holder's inequality based on this Young's inequality. So for that, let us take, let's say, let us take A to be the norm of f of x divided by this quantity, okay, and B to be the norm of g of x divided by the corresponding LQ norm. Okay. Then if you take, let's say, the product of these two, and by Young's inequality, the product AB, which is norm of f of x times norm of g of x divided by the two denominators is less or equal to 1 over p a raised to p here we should have x and y, but let us remove this x and y for simplicity. Okay. Plus 1 over q times a b raised to q. So that would be g of x raised to q divided by the LQ norm. Okay, so integrating over x, we would have the following. So the integral here of the numerator would be the L1 norm of the product. Okay. By linearity of the integral, so you have this part here. Okay. Now, if you integrate this one, that would be precisely the norm of f in LP raised to p. So on the left-hand side, for the first term, you end up with 1 over p. Okay. And on the second term, similarly, if you integrate this, this would be the LQ norm of g raised to q. So it will in turn, cancel. Uh, you can cancel these two, and you end up with 1 over q. This is equal to 1. And you can see now that L1, by multiplying both sides, this quantity, we have this. Okay, so and this is Holder's inequality again, since here so far we assume that R is equal to 1. So I would like to emphasize here, okay, that this assumption or these quantities are positive due to this assumption here. So in order for A and B to be well defined, we need to assume that these norms are none or not equal to 0. So A and B are well defined. Okay. So going back to the proof of Holder's inequality, so far, if you can notice here, R is equal to 1, R is equal to 1, and R is equal to 1. So what if R is not equal to 1? And that would be our final step. Okay, so step 3. We now consider the general case. So again, suppose that 1 over P plus 1 over Q is equal to 1 over R. So I want to reduce this in the case of what? Where R is equal to 1. So we do that by dividing R on the denominator. Okay. So if I take or let's say P tilde to be P over R and Q tilde to be Q over R, based on this inequality, then the sum of the reciprocals of this P tilde and Q tilde is now equal to 1. Okay. So by step 1, or steps 1 and 2, okay, we already know that the Holder's inequality is valid when R is equal to 1. Okay. And in this case, we now have the following. So the L1 norm of the product is less or equal to, okay, so we need to, okay, so the LR, let's start with LR. And write this in terms of the integral. G of R d mu. Okay, so this is just only the definition of the LR norm. Now R is equal to what? Based on this inequality here, R is equal to P divided by P tilde. Okay, and similarly, R is also, using the second inequality or second equality, Q divided by Q tilde. So we will apply the Holder's inequality. So here you will get what? The LP norm or I should say LP tilde norm So let's raise this to the power p tilde 1 over p tilde, because that would be our exponents in this case. Okay, times, well, you could do that on the second term, q divided by q tilde raised to q tilde d mu 1 over q tilde. Okay, so you can see that this will cancel. I can write this, let's say, uh, in terms of what? Or 1 over p tilde is equal to r over p, according again to this inequality. And similarly, if you use this, you will get r over q. So let us summarize the left-hand side. So we started with the L1 norm of the, or the LR norm of the product. We have shown that this is less or equal to, okay. Here, take note now that the power is p. I have a reciprocal here. So this will correspond to the LP norm, but then I have an extra power r. So this should be raised to r. And you can do that for the second term, and you can observe that this is the LQ norm r, or LQ norm g raised to r. And you can now cancel this r, and you get the Holder inequality. So let's cancel this r, and that's it. Okay. So this is the end of proof for Holder's inequality. Okay. So just to remind ourselves, we use the Young's inequality to establish Holder's inequality. And what is the purpose of Holder's inequality? For us to show the triangle inequality. In the case when P is finite. Okay, so let us look at that. And in fact, it has a special name. So the triangle inequality in LP is known as the Minkowski's inequality. Well, this is nothing but the triangle inequality, in fact. So the norm of the sum is less or equal to the sum of the norms. Take note that we already showed this in the case where P is equal to infinity. Of course, F and G must be in this Lebesgue space. So that's the triangle inequality. So the triangle inequality in Lebesgue spaces is also called Minkowski's inequality. Okay, so let us look at the proof. How does the Holder's inequality enters to this one? First, okay, this is done because we have established this a while ago. So suppose, let's say, P is finite, and again, assume that the left-hand side. Okay, we will not emphasize x and y now. Suppose that the left-hand side is strictly positive. Okay, because if this is 0, then trivially, since these functions are non-negative, this inequality is valid or trivially holds when the left-hand side is 0. So let us suppose that it is positive. Then, okay, let's start with the left-hand side. Now, to simplify things, let us first raise this to power p. Let us apply the definition. Okay. And then there's a clever way to write this. So first, let us write it in this way. P minus 1. So take note that P is greater than 1, so P minus 1 is positive. Okay, so we split the power P into two parts, one with power 1 and the other the power P minus 1. Okay, so simply applying the triangle inequality and the linearity of the integral. So you will have these two parts here. P minus 1 d mu. Okay, so let us concentrate on the first term. Let us consider this one. Okay. So let us write that down. So we copy this term. And in here, we apply Holder's inequality. Okay. Of course, Q is the conjugate of P. So applying Holder's inequality, we would have, okay. So for the first one, we take the LP norm. And the second one, we take the LQ norm. Okay. And for this, let us apply the definition. So this is the norm f plus g, p minus 1 raised to power q, d mu 1 over q. Let us do some arithmetic with regards to the powers. So 1 over q is equal to 1 minus 1 over p. And this is equal to p minus 1 over p. Therefore, we can see that product of p minus 1 over times and q. So you cross multiply, that is p. Okay. So therefore, this part here is in fact equal to p. And we can write this, okay, as, let's say, p over qp. So we can write this as 1 over p times q over p. So that here we will get the LP norm. Okay. And at correction, of course, this should be LP. So with this, we can write down the second term as the LP norm, because now the power here is P, and then you have the reciprocal of P here, but you need to adjust this to Q over P due to this extra power. Okay, so with that, so that that estimates the first term, and you can also do it in the second term. So summarizing, okay, with that part, or combining. So let's go to the next part, the next page. So here you have what? The LP norm. Okay, this is less or equal to. So this is what we have shown so far. This is a P over Q. And you do that for the second part. You replace F by G and you end up with the same conclusion. Okay, so here you see there's a common factor. And if you divide both sides by that, we will get, okay, P minus P over Q, LP, less or equal to the sum of the LP norms. You factor and then you divide the common factor. Now, notice that P minus P over Q, well, P is a common factor, so this is P times the quantity 1 minus 1 over Q. But since Q is the conjugate of 1 over P, so 1 minus 1 over Q is 1 over P, so this is 1. So therefore, we can make this as 1, and we get the Minkowski's inequality, or the triangle inequality in Lebesgue spaces. So this is the end of proof for Minkowski's inequality. Okay, so this verifies the triangle inequality, as I said. So we can now conclude that this, well, finally, this is a norm on LP. For any P greater or equal to 1, less or equal to infinity. So in the next lecture, we now show the completeness of the Lebesgue spaces.